Hey everybody, we got a circuit diagram. Let's draw the schematics first. We have a voltage source with a sine wave, and the load is a series of a resistor and an inductor. In parallel to this is a capacitor. Let's talk about a little bit what we have here already. It's called a True Parallel RLC circuit. Why true? Because this represents a motor, and the capacitor is there in order to compensate the reactance of the inductance. The goal is to bring the current in phase with the voltage. It's called power factor, or real power, or reactive power. We don't care here about right now. It's a different lesson. This circuit has an entire impedance. Every branch has a different impedance. The resistor has an impedance. The inductor has an impedance. The capacitor has an impedance. We got two questions. Question number one is, what is the function of the current and dependent on the time? Question number one. Question number two is, what is the current when the voltage is at the phase angle of 60 degrees? How to solve this? We have Ohm's law. Ohm's law says the current is the division of the voltage by the impedance. Bear in mind, everything is a vector. It's a complex number. The phase is important to know. We have a sine wave, so that we can say I as a function of the time is something with the sine wave, omega t. What is the magnitude? In this case, it's the magnitude of the voltage divided by the magnitude of the impedance. The impedance has a phase angle, and therefore we have to consider this in this formula by changing with the impedance phase angle. The other way to solve this solution is we should know the magnitude of the entire current. Again, a sine wave plus the phase angle of the current. This tells us also already we have two different options. This is option number one to calculate, option number two to calculate. What we have to do is, the voltage we know, it's 120 volts. We have to calculate the impedance, or the other option is to calculate the current, the sum of all the currents in the circuit. To be honest, it's a little bit easier, option number two. Why? Option number one needs the calculation of the parallel resistance. The parallel resistance of this one is the product of both branches divided by the sum of both branches. This can be a little bit tricky, a little bit more to do. The easier way is actually to go via the sum current. If we see the current here, what is the sum of this current? I draw the current like this. Let's say this one. I give it this direction. So the RL branch, and the current, so the capacitor, is this one. IRL. IC. I give it a different direction because, you know, on an inductor, the current lags by 90 degrees. Therefore, I give it this direction. And on the capacitor, it leads by 90 degrees. Therefore, the current has different directions. One cross-check already. If you have any current here in these branches, the sum must be smaller because the direction is different. They cancel each out, so that the sum of the current must be smaller than the maximum of either of these branches. Okay, let's go with option number two. We need the total current, which is the current through the RL branch, plus the current through the capacitor branch. What is the capacitor current? It's again Ohm's law. It's the voltage divided by the impedance of the capacitor. Similar in the RL branch, the current is the voltage divided by the impedance of the RL branch. What is the impedance of the capacitor branch? It's 0 because it does not have any resistor. Minus J and then 1 divided by omega C. The impedance of the RL branch is the sum of the resistor and the inductor, the resistor plus J omega L. And now when we calculate these terms and we do the calculation and the triangulation, and the phasor diagram would look like this. We have here our real part, imaginary part, everything is for the current. We get our current through the capacitor, which leads the voltage. The current through our inductor would be negative, like this, but in series with the resistor, it's a little bit rotated, so that we have actually here our I of the RL branch. If we do the triangulation and the mass in the Cartesian format, we get a resultant current, this one, with an angle phi, which is minus 9.45 degrees. Okay, and now we can use, for the second question, we can use this. We would know the current at the 60-degree angle is the magnitude of the entire current. The sine omega, we use 0 as the time because we consider the voltage directly without any phase shift, plus the phase angle of I, but the phase angle, plus 60 degrees, plus the phase angle of our current. This one is the difference. It means 60 degrees minus 9.45 degrees, and then we figure out the current when the voltage reaches the 60-degree phase angle, and the result is 1.46 amps at this point when the voltage is at 60 degrees. What's very important to know, this value here is the peak voltage, and the peak voltage is actually the real momentary value. This voltage here given us is in RMS, and you would know, okay, the relation between effective or RMS voltage and peak voltage is the square root of 2. Therefore, we do all the calculations with the effective voltage with RML values, but at the end we have to multiply our results with the square root of 2 in order to get the real peak voltage. Okay, thank you.